infrastructure providers for a decentralized network and a decentralized world. And you're going to hear from all the people here: Fluence, obviously, Spheron, Gensyn, Filmine, Streamr, and Lit. And follow kind of a normal element. We will start last is first. So Lit is on the far left, but we're moving them first. David Snyder, founder of Lit, is going to introduce it. It's a decentralized key management protocol, which has huge implications for keeping data safe and managing data securely and in a decentralized manner. So with that, I'm going to turn it over to my friend David.
Thanks, Tom. Really appreciate the Fluence team for inviting me here, and thank you all for attending. As mentioned, my name is David, and for the next several minutes, we're going to talk about key management, specifically decentralized key management. So to start, by a show of hands, does anybody recognize who this is? Yes, excellent. And so another way to think about who this is from the perspective of key management, this is a centralized trusted custodian, if you are familiar with this film. And if you know how the story goes, it is that centralized custodian, this is from The Matrix, that gets compromised and lets Neo into the source. And just using this as a kind of a fun example to illustrate some of the issues with centralized custodians. It's not just in Web3, but also in the world of film. And so it really comes down to the question where are the keys stored? So in the Matrix example and in many examples across the internet, keys are stored centrally in key management systems, or of course self-custodied by individuals who want to interact with distributed systems or privacy systems like Signal Chat, for example. And then for us, in the context of building a distributed key management network, where are the keys stored? Another way to ask that is, can the internet keep a secret? Which is a big question that has been floating around this space for a long time. And I'll tell you about our attempt to let the internet keep a secret, as well as what that can be used for. So first, a little bit on the network itself. This is, as mentioned, a distributed key management network. There are 3 core components that I'll quickly go through that make this possible, that are listed here. It's a DKG, which is distributed key generation. That is a cryptographic process where a bunch of nodes can come together. They exchange polynomials, and as a result, each of those nodes now custody something called a key share. That key share does not represent the entire cryptographic secret, but a threshold is set whereby 20 out of 30 nodes, for example, or in the example of like Coinbase's dApp browser, they do a 2 of 2 scheme, but the scheme is tunable where you can say you need X of N of these key shares in order to use this underlying distributed key. So that's one of the core cryptographic primitives at the heart of this network. The other one is something called PSS, which stands for proactive secret sharing. And sometimes you hear this referred to as a key refresh. And so the problem that this solves is, okay, you have 100 nodes, they have this shared distributed key, 70 of them need to sign off or authorize any action with this underlying distributed key, but how does that network persist over time? How can you ensure that nodes can join and leave the network over time? And that is where proactive secret sharing comes in, which is a method for assigning out new shares to the next epoch of node operators, where you can maintain the same underlying secret, that same underlying elliptic curve in the example of Web3, but have a different set of parties holding that secret in distributed custody. And then the final element that makes this network complete is the use of secure encrypted virtualization. It's kind of like an enclave. It is a black box. And so all of the nodes in this network perform all of their operations inside of SEV. And the role of that is to prevent the node operator from ever having access to any of that private key material, which in this case, as we talked about earlier, is that private key share. And the top 2 things, DKG and PSS, typically, like these are these are subcomponents. Typically, you hear this referred to as threshold cryptography more generally. And then the overarching category that these processes are part of is something called MPC, or multi-party computation. So another way to think about lit is as MPC key as a network, or a distributed key management network, as we've been talking about. So now let me tell you about how it specifically works. Just like with public key cryptography, so independent of anything distributed, just with an asymmetric key pair, a key pair basically gives you two core features: the ability to encrypt stuff, like how Signal works, and the ability to generate digital signatures, like how MetaMask works when you want to sign a transaction and push it to a blockchain. And so I'll talk about both of those features in the context of distributed key management, first starting with encryption and decryption. And so what we're looking at here is an oversimplified diagram, but basically the way that the process works is Alice can encrypt some data client-side. So let's say it's like a video. Alice can encrypt some data and go and store that on IPFS, on a blockchain, on Arweave, wherever. And with that symmetric key that's generated client-side from Alice, Alice can encrypt that to lit, which again is a key pair in its own right, and set a rule. And so some of the rules that we've supported thus far are based on blockchain state data. So developers can say, hey, let somebody get this key when they hold certain assets in their wallet. And so this is like an oversimplified way to describe this is like token gating. So you could say somebody needs to hold this NFT in order to decrypt this content. And so the cool thing about it is the decryption. So Alice encrypts that data, she encrypts that video, she sets a rule that says only somebody who's a member of my DAO, for example, can decrypt this video and view it. Bob shows up later on. Bob is a member of a DAO. He signs a message, which is his proof, and he broadcasts that to the nodes, to the lit nodes. The lit nodes then, as we can see here, validate that data against the blockchain. Is Bob a member of the DAO? And then if yes, each of these nodes generates something called a decryption share. You can think about it as like an authorization, and sends that down to Bob client side. And this is what's really, really cool about MPC is it's almost like a client side consensus. There's no interaction between the nodes. It's like a nice mental model is similar to the way torrenting works. But rather than Bob collecting little bits of a movie, what Bob is collecting is little bits of the ability to decrypt that symmetric key. So Bob collects all those decryption shares client side, and now he can decrypt that symmetric key that Alice initially generated, and then use that to decrypt the video, and yeah, he's in business. And so now we'll walk through a couple specific, oh, yes. One more thing I want to mention before we get to the use cases is it's not an exact definitional match, but this is kind of like what they would call identity-based encryption. And I pulled this page from Wikipedia, and as you can see, like identity-based encryption to date does require a central authority to do that key provisioning. And that's the invention that we have here, is being able to do the key provisioning but without a central authority in this threshold-oriented way by dividing the key up as we discussed earlier. And now let's talk about some of the use cases. So if you're familiar with Lens Protocol, it's an NFT-based social protocol. Inside of the Lens SDK, they have the notion of gated publications. This is a screenshot from the Lenster app, where when somebody makes a post, they can say, only collectors can view this, or only people who follow me can view this. And it's the same process that we talked about before, where that poster or creator, that content is encrypted. In the Lens case, it's stored on IPFS, and then lit is being used to validate, does somebody hold the follower NFT, or does somebody hold the collection NFT? And if so, they're able to decrypt that content. This is also being used by Orbis Club, which has built out a social graph and chat interface using Ceramic as the storage mechanism. So similar kind of mechanic. This is a screenshot from the Orbis SDK. And so lit and the key provisioning that we're talking about here is being used in the context of token-gated messaging and chats. We'll see if this is going to play, but I'll be able to talk you through it. So what we're looking at here is quite cool. This is an example from a team called Crebit, and what they're doing is using a third-party vendor to Oh, yes, full screen. Good idea. What we're seeing here is they're using a third-party vendor to validate some KYC information. And then that KYC information, that proof of somebody's age, for example, is going to be encrypted client-side and also signed by that vendor, and then in this case, stored on Ceramic, and then that user gets selective disclosure around who can decrypt that information. And so, like selective disclosure, I just want to define that for a second. A kind of a Web 2 analogy of what selective disclosure is, if you've ever signed in with Google, and you see that screen that says, hey, we would like access to your contacts or your calendar or whatever these scopes might be, that's obviously if there's three parties in that system. There's the user, there's Google, which is custodying the data, and then there's the third-party app that wants that data. In this example, that's zero-party data. That data belongs to the user, and then they can have a direct relationship through provisioning a decryption key, who in this case can see who can decrypt this KYC information. Just in the interest of time, I'm going to continue to move along here. And then I know the team from Streamr is talking later. They've been up to some really cool stuff around using this key provisioning mechanism. Conditional decryption is another way to think about it. Access control is another way to think about it for having a distributed data marketplace. So that is some use cases and how the encryption works. Oh yes, and then there's one more feature that this actually I just put this in last minute. This got released 2 days ago. So for about the past year and a half, the SDK was set up to only be able to provision decryption keys or perform the access control based on any state data. It is now possible to have this network provision decryption keys based on any HTTP endpoint, any API. So really any data on the web can be essentially used as the input for an ACL or access control list. And this feature is called lit actions conditions. And I'll talk more about lit actions in just a moment when we get into some of the signing stuff. And so the product around programmable signing, and again, just going back to the framework that I talked about earlier, with public key cryptography, you have encryption and you have signing. And so this is kind of the other core feature of public key cryptography. We have this product called a programmable key pair. And what it is exactly what it sounds like. It is a distributed custody wallet, aka key, that can sign based on rules. And let's take actually a look here. I want to show you what these rules look like. So these rules are encoded in JavaScript. And what we can see here is a JavaScript function where it says sign ECDSA. I don't know if you can see that here. But basically, it is a mechanism in a single function to say, I want this distributed wallet to sign on these conditions. For example, well, actually, we'll go ahead and look at some examples. For example, in the context of creating wallets for users, so user onboarding or what you might call retail custody. So what we're looking at here is a few wallets being generated via OAuth credentials. So the user in this example is not custodying any seed phrase, but also not reliant on a centralized custodian to hold onto the key. And that one is really, really cool. Really excited for that as it relates to mainstream onboarding of Web3, using this distributed key essentially as the user's wallet. And there's a lot of really interesting things around like where this touches account abstraction as well. Another really interesting use case is around DeFi automation. We'll see how much of this you're able to see, but this is a project that a community team built for using one of these distributed cloud wallets to basically function as an immutable and automated escrow agent for cross-chain swaps. So Alice sends some tokens from Polygon into this wallet. Bob sends some tokens from Arbitrum into this wallet. And then when they both approve, the wallet, because it can sign programmatically, sends the requisite tokens to the appropriate counterparty. And so if you think about like OTC deals, over the counter trading of tokens, this would be a mechanism for not having to have like a trusted escrow agent, but basically having code as the escrow agent between blockchains. And what's being shown in this video is just the process for sending the tokens to this programmable key pair, and then approving it, and then receiving them. Awesome. And then the swap is about to happen. And all of this stuff is on our Twitter. If you want to look at these videos, we put out a lot of content as well. And then this last one is from Crebit as well. This is really cool. If you're familiar with what verifiable credentials are, it's basically some signed JSON linked data. In this case, Crebit, as we talked about, stores this data on Ceramic, but it's like, who is the signer of that verifiable credential? What is the key that you trust? And so what we're looking at here is a user who is connecting their Discord, and then it is this MPC network that is signing that. And so this user can basically add, in a privacy-preserving way, their Twitter name, their Discord name, et cetera, to their data backpack as a signed verifiable credential. And the signer of last resort isn't the user, because how can you necessarily trust it's one user versus another, but it is, again, this distributed signing mechanism. And then, so I'll kind of end this to say, where are the keys stored? Coming back to this key question, and it's really interesting. So we're right now in the midst of rolling out the network. There's a handful of node operators, and I just want to kind of make a mention that if you want to operate a node in this network, there's a contact us form right on litprotocol.com. We are like right in the midst of rolling this out. So if that's something that you're interested in, please do get in touch. And maybe I'll have a time check here, but if there's maybe a few minutes for questions, I would be glad to take them, and thank you so much for your time and attention.
If anyone have questions, let me know.
There is
Yeah?
a question, but I think I lost the mic.
Yeah.
Oh, there it goes. Hey, so the question is, how does this differ from NuCypher and Threshold Network? So what they're doing is something called proxy re-encryption, where the input to that function is a key. So I could say, this key used to be encrypted to person A, but I want it now to be encrypted to person B. And so the input is a key. And so that person who wants that key to be re-encrypted to another party needs to be online. It's very, very interesting technology, but for the specific use case that we were trying to solve around conditional decryption, we actually looked at using them a few years ago. It didn't quite meet that, which is why we went through this MPC key provisioning mechanism. But yeah, it's really cool, but basically the difference is that in proxy re-encryption, you start with a key and it gets encrypted to another party, where in what we're talking about here around conditional decryption, the key is encrypted to the network and the input is a rule, and then the output is that same symmetric key.
Okay. So I have a question that how is it different from the REN BTC's MPC? How is it different from the REN BTC's MPC?
REN BTC NPC?
Yeah. So REN BTC is also doing like that. So how is it different from that one? And also, can you elaborate on the part that what account abstraction and multisig would do to these protocols?
Yeah, absolutely. So I'm not that familiar with this protocol, so I can't talk to that in detail, but I'd be glad to chat with you right after this and learn more. As it relates to account abstraction, to me, probably the most interesting use case that I've seen around combining MPC keys with account abstraction or smart contract wallets has been around user onboarding. There's a team called Patch Wallet, where basically they have set up an AA or account abstraction wallet where a user who's new to Web3 can sign in with Twitter, and the MPC key acts as the signer on the AA wallet, and then it lets the user move to self-custody over time. So once they aggregate some assets and some reputation, they go, you know what, I've had enough of this MPC key, I want to move to a hardware wallet. They can call a function to boot off the MPC signer and move to self-custody, and it's a pretty interesting on-ramp for individuals that are entering the space. We'll talk more about REN too.
Any other questions? Yeah.
Can you speak a little more to the type of conditions you can have? Like you said something about HTTP endpoints, but can you query a contract state, for instance?
Yeah, so let's take a look at some of these conditions. So the conditions, like on EVM chains, for example, can be any, like here's an example of somebody needs to hold an NFT within a given collection, but also any kind of custom contract can be used as the input for designing this condition. So here in the Moloch DAO contract, they create the construct of a share, and here you say if somebody has one or more shares, they can do the decryption. And then the new piece that I was just talking about in terms of using even off-chain data, it's writing that function in those lit actions that we were talking about earlier, that JavaScript, and that can be connected to any data, on-chain or off-chain, and then return a true or a false, and that's just encoded in JavaScript, and you can connect to any point there, and then you can basically have the lit node say, if this returns true, based on this JavaScript execution environment, Turing complete, connected to anything, provision the key to that individual.
I saw someone were. Yeah. Any other questions? Yeah. Okay.
Hi. I just have one very simple question. You mentioned earlier there is a use case that so the content creators can use semantic ways to encrypt the content information.
Correct.
And Bob, which is a DAO member of Alice, can use some way to get this semantic keys from your distribution node. So there is a question: is it possible that Bob could leak this semantic key? Because we all know that once you create a semantic key and it's leaked, all the information will leaked online. Is there a way you can create some kind of time-based semantic key which gonna change over time?
Yeah, so certainly you could implement something around key rotation, but it's a very interesting question. And the question is, once somebody has that symmetric key or their content, what's keeping that from putting it on YouTube or doing anything with that? And frankly, there's no kind of obvious solution there. So if you think about Patreon, for example, somebody subscribes to a Patreon. If I'm a patron of Mr. Beast, I can screenshot or screen record that video. So they have access to the key and they have access to the content. The reality is that somebody's own laptop, their own client, is their environment, and they can take the content at that point. One more question, maybe?
Yep. So we haven't talked a lot about the nodes, but at the beginning you've hinted at at them using secure enclaves in order to not leak this information to the node runners, right? So what type of enclave are you using? Because SGX has been pwned several times, and it doesn't seem to be standard for anything.
Yep.
So how you solved?
We're using AMD SCV SNP. It's the same processor that's used by Google Confidential Compute and HashiCorp. Banks use it. It's pretty new technology. If you're interested in this type of stuff, definitely worth taking a look at secure encrypted virtualization. It's technically different than an enclave. And the specific use of that, it's not the primary method of security. The primary method of security is distributing the key, but it's functionally a backup method. And my personal take is that anybody that's working on distributed MPC absolutely needs to be using some kind of encrypted virtualization or enclave, because it starts to get really scary if the node operator can be doing something with the private key material. AMD SCV SNP.
Great.
Amazing. Excellent. Thank you so much. You're
Let's
awesome.
give Dave another hand. Thank you. Fantastic. Up next will be Evgeny, who is a co-founder with me of Fluence Labs. Fluence is a distributed serverless compute network. And I think all the companies that you're going to see, all the protocols you're seeing today are critical and all function together. Fluence is unique in being just the compute piece of it. And Evgeny is going to go into a lot more detail about what that means. But one thing I will tell you, it's not just compute at the edge, and it's also just not a compute that happens where the data is. What's critical when you have serverless compute is that compute has redundancy and is built-in failover resilience. And that is what I think has been missing in a lot of the distributed compute protocols that have kind of been out there so far. And that's the problem that Fluence is working hard to solve. So I just stole a little bit of Evgeny's thunder here, but I think he's got plenty more to talk about besides that. And I think he's ready to go. So with that, Evgeny, do you want to take this mic? And with that, Evgeny Pomerov.
Hello. So yeah, I'm going to talk about Fluence. So like basic introduction, it's kind of obvious things. We are moving into world of decentralized platform, decentralized compute in particular. And if you think of how compute projects in Web3 space were designed, like the first most innovative for blockchain, the new type of compute where you have consensus, but because of consensus, it's kind of restricted and slow and kind of useful for specific use cases like digital value. And then there was the generation of projects building using blockchain to create compute marketplaces, and basically it was about hardware marketplaces to aggregate a lot of compute resources and solve all the problems of humanity, like big scientific problems, or like applied to some computational heavy tasks like rendering video, for example. But we've been looking for some solution that would allow us to have some general purpose compute infrastructure to put our application backends on, or basically whatever we have right now in a Web2 space, in Amazon, in Google, in the clouds, to put it somewhere to run the actual code somewhere securely and in decentralized fashion. Obvious thing. Platform risk in Web2 space. If you build it on the cloud, they can shut you down, they can censor your account. If you're using some big social media or a big platform API, like ChatGPT, for example, or more older Facebook APIs, they can shut you down, they can censor you, you can lose business if your business depends on particular API provider. But we see similar things happening in Web3. As we see, stories about Tornado Cash with all their accounts in GitHub and everywhere shut down. We see how MetaMask and Infura censor IP addresses, and kind of some people basically lose access to the infrastructure, and that's kind of not cool. We want to have something more resilient and more universal, more permissionless and open for everyone. And similarly to Web2 API dependency and platform risks, we have similar things in Web3. Like today, many companies in Web3, when they build their products on top of on-chain data, usually their products, if they ship their products as APIs for developers, these APIs being hosted on particular servers in particular cloud, usually managed by the team who runs the project. And it means that whenever any issue happens, any government pressure or bad day in some of their team members, they can shut you down. You can lose access if you're using their API. You can lose access. But it's not because all these projects are bad. It's because there is no just proper infrastructure that you can use to create your API and share it for other developers the way that you cannot really cut access from them. And yeah, so we see decentralized computing like a kind of solution to solve this problem, and it sits somewhere in the middle between, in terms of capabilities between on-chain and centralized computing. For example, it doesn't have any middleman, doesn't have any particular company that operates the network. So you should be you should feel good as you are not dependent on particular provider. At the same time, it's verifiable, but it's not constrained like a blockchain. If we have such infrastructure, then it's useful for many things. We could do whatever we could do whatever applications we want to manage by DAO, because like if they are not in proprietary cloud, then the DAO can make a decision about like application upgrades or like some changes and stuff like that. So it could be like immediately enforceable. You could build all kind of trading bots. You could think of distributed validators, MPC, RPC relayers, indexers, oracles, all kind of things. And also you can think in terms of like a standard ideas about, hey, let's do better messaging, social media, and stuff like that, because like you need some infrastructure to build this. And basically, this is what Fluence enables you. And Fluence is two big parts. So it's a developer platform giving you tools, and it's a computer marketplace organizing computing resources from different providers into a network, so you can deploy on these resources. And so again, Fluence is cool because it's permissionless, potentially lower cost than clouds, censorship resistance, less dependency on vendor lock-in, and secure. Couple of words about developer platform. So we're trying to replicate kind of experience that everyone used to, and best experience in the cloud is serverless. So what we have is basically several tools that you can use. Like, for example, Marine is a WebAssembly runtime. You can think of Marine as an analogy to Lambda. It's a little bit not the same thing, but it's a useful analogy. We have Aqua, which is our distributed execution protocol and the language, but it's kind of similar to Amazon Step Functions or Google Workflows, which you use to express your business logic on top of Lambda functions. And then there are like some other tools that also kind of similar to traditional cloud stack. So a couple of things about how it all works under the hood. Like usually in the cloud, when you build an app, you usually have several microservices that gate it by some API gateway, and your users, client devices, they talk to backend through a single API gateway that runs in the cloud. And Fluence implements the coordination-free distributed execution protocol that allows you to, whenever business logic you program, it allows to execute it over the network of providers without any centralized gateways. So literally, your app is being executed without, getting back and forth to single place. Aqua exists as a scripting language that allows you to express algorithms in terms of distributed network. So you can say, for example, if you have some tasks where you need to calculate some average of, let's say, Bitcoin price, you can have the function that executes calculates the price on one machine, and you can have several such nodes that only host this function and only provide this function. And then you have other machines, other nodes that provide function that does average, calculates average from the prices. And then you have this script saying, I want the input data to go first to nodes that calculate the price, and then force them, after they calculated the price, to send this data to nodes who calculate average, and then to the calculated average to send to the another user or some output database or somewhere else. And this will be executed by the network, by these participating peers, without any central coordination. They will not be sending data back to initial client. They will not be sending data to some blockchain or somewhere else. It would be just coordinated over the network. And Aqua is super useful to build all kind of distributed systems from the ground up. So from simple things like a peer discovery, resource discovery, to things that we used to have in the cloud, like fault tolerance, load balancing, failovers, auto-scaling, and stuff like that. So basically, what we have right now, like some of the things exist right now, and some of the things end up to like we commoditize some of the things into more general concepts. Like for example, we introduced concept of subnets, and subnet is basically the on-demand subnetwork of nodes that are providing some piece of application. For example, subnet could be like replicated, having consensus provider of some data. For example, you can have like a IPFS subnet. If you want a fault-tolerant provider of IPFS data on Fluence network, you just rolling out IPFS subnet, and then every node participating in this IPFS subnet will be connected to IPFS network, and they can optionally have consensus on top of data. They may not have consensus on top of data. You can basically program and customize the coordination mechanism between these nodes in the subnets. And by default, Fluence right now, when you deploy your application, your function on Fluence, it will be deployed to on-demand subnet. So the nodes will opt into providing your function. They will coordinate with each other, and you can customize the way they coordinate. You can implement it with basically writing Aqua algorithm. So like Fluence network is heterogeneous. So every peer is different. Every node is different. It could host, like every node decides basically whatever applications or functions it hosts, and every node can announce and advertise that okay, I can provide access to this and this external things like data or like a blockchains or external APIs and stuff like that. So every node can be connected to external data and then provided into the network for the functions that run in the network. So the next thing is computing marketplace, which is, you know, if you're familiar with things like Filecoin is a marketplace of storage provider. We're building marketplace of compute providers, and basically like if I have some compute capacity, some servers, I can join the network. I can say, okay, like my I'm gonna charge this amount of money for my resources, and also I'm gonna provide these types of data for applications on the network, and then I compete with other providers. And basically, whenever I deploy my application, I can deploy it to many providers at the same time by rolling out subnetwork. And the other thing is we like basically when we think of decentralized computing infrastructure, we think a lot about security. Like how do I, like if anyone can join the network, anyone can be a provider. How do I trust whatever they execute, right? So in many solutions that we see on the market right now, it's basically I have to trust the provider. I have to trust that they're gonna do the work correctly. And what we are trying to do is we're trying to bring cryptographic proofs to any types of execution. And because of the design, how the Fluence works under the hood, because of these Aqua and Marine components, we have several types of proofs. We have proofs on Aqua execution, which is like a proof of this distributed this distributed execution were executed correspondingly to the script, and all the nodes that executed every piece of it, signed the data correctly. And so the flow of the computation is correct. Then the other part is that the function that every peer was executing is correct. That's the proof of execution. And then the other thing we want to bring is capacity incentives, which basically when providers will prove that they own some amount of compute capacity, they can prove that they own it at some moment of time, and then based on this we can like incentivize them with tokens to be on the network, to grow the network faster. How, like where we are right now, basically all these proofs are so proof of processing, proof of Aqua is coming soon, like maybe in a couple of months. All other proofs are down the road. In terms of like developer experience and developer platform, we are much more advanced. So this week we are hosting several workshops where we'll be showing the developer experience using Fluence, and it's kind of like what we are releasing this week is basically the smooth experience, so you can create projects and deploy it easily with like a couple commands. And under the hood, it would do all the complex work. It would create the subnet from the nodes on the network. They will actually participate in the compute marketplace that would be like hidden from, basically like abstracted out from developer tooling. So they would, under the hood, would put some like token stakes that would coordinate into the compute deals and stuff like that. So like basically, the state of Fluence right now is developer tooling is advanced, so you can build applications, you can deploy on a network. The compute marketplace is on a testnet, so like all the deals and stakes and stuff like that, it works, but it's not live on the mainnet. And then like we're gonna work more on implementation of proofs, security, and moving the compute marketplace on mainnet after proofs are ready. Yeah, so some of links, obviously, and a couple of things that also I wanted to cover. We're gonna host this several workshop this week, where we'll be showing the one of the example applications, like the simplest application that you can create on Fluence. It's a distributed RPC resolver, basically. It's sort of decentralized in Fura, built on Fluence. It's an app that, when you use it, you can deploy your own instance of RPC resolver that you can use with your Web3 app. And under the hood, it would be load balancing requests to different RPC providers that you can specify. Basically, this is like this RPC, these nodes that providing access to RPC providers would exist as a subnet on Fluence network. And all the RPC requests from your DApp would be routed through Fluence network to one of these RPC providers based on the Aqua algorithm that is written into this example application and that you can customize. So we have bounties, feel free to check out. Yeah, and other events, workshops, join us this week. Yeah, thank you.
Thank you. Any questions to Evgeny? Yeah, 1 minute. Can we have mics a little bit louder because we hear in the second stage more?
Hi. Yeah, it's very cool. I love serverless. I mean, I think serverless is very cool. But I have two questions for you. First is that in today's computing services, in cloud services, serverless is not entirely replace all the computation. Like in AWS, still I think more than 17% of the computing resource comes from EC2, not from serverless. So the first question is, how do you think the future of the Web3 of the computing? Do you expect that the developers will use all their computational power and their resource in serverless, which I don't think is possible? There is still some kind of computational task which serverless cannot take. So do you require the developers in the future gonna do a combination of the Web2, EC2 plus the decentralized serverless to do the sense?
Yeah, well, basically we are looking at Docker as well, right? Like so the thing is, like you can create secure system if you have basically like if you build on Docker, it's super hard to make it secure. It's super hard to build proofs for the execution of Docker, and you have a lot of other issues with slow start of Docker containers and the amount of memory they take, amount of resources they take. So, but I agree with you. Like, you cannot put everything in serverless.
Yes.
So, like, mainly right now we are focusing on WASM and serverless experience. But like at some point, Docker will be there. It's just like will be a little different security model for running Docker on Fluence.
Okay, my second question is about the security. Because when we're running something, no matter it's in EC2 or serverless, sometimes we have to put some like security stuff inside, like a connection stream to the database, or some kind of a key to the API call. So in your serverless computing stuff, how could we trust that we can safely put those connection stream or the security key inside this random node? And also beyond that, you mentioned about you will do some proof of something to guarantee it's going to be execution by the way of the script. But how could you going to guarantee the node won't link the information or data during the runtime out?
Yeah, that's a good question. So with secret keys, we are like, it's coming also, like it's not there yet. So right now, basically like you can pass the key to the node, to your function, and deploy this function to the node, but then the node will be able to like, scan memory or something and just see the key. So the solution is basically like end-to-end encryption. So you protect it from at least network nodes not seeing your key, and then using like secure enclaves on the nodes, so like the node doesn't, cannot access your key, and then it still leaves some sort of trust to the node provider, because like you still trust the provider that they run proper secure enclave and stuff like that. And the only other option basically that exists is you always use MPC for signing whatever, for accessing whatever external APIs, and the nodes on Fluence Network should only get the shares of the key, and that's the solution.
Okay, thank you.
Yeah, thank you. Yeah, love your presentation. So I'm really curious, like, if you could elaborate a bit more about how the execution flow or how actually the deployment flow works. Say, I want to deploy something like BFT related, right? And then how do I contact with your P2P network? And in the process, right, say the nodes are executing some BFT logic, and then like some nodes goes offline. And how do you like do the fail over? And in the process, like, do the nodes like they just talk to each other and know each other's like performance ranking? Like, how does that process work?
So basically, your BFT algorithm is part of your application. So like you write the you have to implement this algorithm of how the coordination between nodes will work, and Fluence Protocol gives you discoverability. It means like when you write this script, you can say, okay, I want to, like, if I see this, peer not available, I should, replicate this to another peer, or I can call this here and there, and then you deploy it to a network. When you deploy it to a network, you deploy it to some nodes. So it means that some nodes will have basically the instance of your application, and after they have it, they can run it, right? So it's a little more complicated, but you can basically you can create cron jobs, right? So you can run you can trigger this script by time. This script that you've written will do whatever you've written. Like, we'll go to this node and send this piece of data, and we'll wait for this response, and then they will. You can write this coordination.
So, say in the case of me running some BFT logic, right? And then some nodes goes offline, and then the nodes that's currently executing will be finding some peer to basically fill up the spot, right? And in the process, like, do they know like which peer is better or worse? How does that part work?
So this is right now is not part of default protocol. So like the protocol doesn't give you automatically substitutions of nodes that went offline or something like that. It has to be part of your application, but we working into for you to have it as a kind of library, so sort of when you build
Got
the
it.
app.
Yeah, thank you.
I saw some other questions here. Yeah, you go first.
In your example for Aqua, it looked like a trustless map reduce. Was that just an example, or is it more than that? Like, can you do more than that with Aqua?
You can do like any distributed algorithms. Yeah, like
Okay.
this was just a map reduce example.
Okay, got it.
Kind of related to the previous question in terms of how the nodes are selected or who does the selection. Say if I want my app to be run by like 5 nodes and then fulfilling certain criteria, right? How is the process of selection done? Or who are the person to select?
Yeah, so if you deploy into Compute Marketplace, which is like a basically public network of providers, you have to make a deal with them, right? You have to negotiate the price, and you have to negotiate whatever you're gonna run on them. So this is a part of deploy protocol that like Fluence just gives you. So this kind of negotiation thing. Currently, at the most basic setup, because the Compute Marketplace right now is not available for everyone. I mean, like for any provider. It's mostly nodes that run by Fluence Labs. Currently, you deploy, like when you deploy your application, Fluence Lab nodes see that you want to deploy it, and like basically a random subset of them say, okay, I'm gonna host it, I like this application, I'm gonna make a deal with it. But this is the part of like making deal. Sorry?
I wonder how's the price right now?
Oh, it's free. It's free.
Oh,
Use
okay,
it.
great, brilliant, thank you.
Yeah, we'd love to hear more questions, and we have time for it. Any others? Yeah, maybe. Oh, Vadim.
Hi. Is it possible to run Tendermint or Cosmos consensus on top of Aqua?
Well, if you implement it in Aqua, yes.
But is it technically feasible to implement it?
Should be. Here's Bernard, who's our chief scientist. You can ask these questions to him.
And is it possible to run WAS modules deployed to Fluence Network on local device? So if I want to just download the package and run it as a WASM at any platform?
Sorry, I didn't get it.
So I want to download some Fluence package to my iPhone and run this application, like maybe this is a bot or a conversion library, or what other application will run on top of Fluence?
Well, you need to have Fluence node to run the application. I mean, like, you need to have Aqua virtual machine, and you need to have a Marine execution, like a WASM execution.
Thank you.
Great, I think we're good.
Great. Thank you, Evgeny. Let's give Evgeny a hand, please. Thank you. And you know, one question that came up earlier I want to address is everything moving to serverless. The way Evgeny had a slide up there earlier, you know, the cloud has a dominant share of compute now, but there's still people running compute on servers in companies, in businesses, right? So it's been a long transition over decades to the cloud, and we expect there to be a transition to serverless decentralized over time as well. It doesn't happen all at once, and there certainly would be applications for which that's not relevant, but over time, serverless will probably take a material share. Happy to introduce Harry, who's going to be talking about a super exciting topic, which is the training of artificial intelligence models using decentralized compute. And I think there's probably no hotter topic right now than the ChatGPT, LLMs. And that has a terrific overlap with decentralization. And I think the further these models get in use, the more important this decentralized training is going to be, and the more we're going to recognize the need for it. Fluence actually fits into this not from a running of it, but or training of it, but from an actual running of the models. And so when you think about LLMs, there's the training, which is massively compute intensive, And I think that's what you're going to hear a lot about from Gensyn and their advantages in doing that. And that has really open source kind of implications as well. But then once they're trained, they also have to be run in a decentralized way because there's lots of censorship potential in the actual running of the models. I'm actually giving a talk on Thursday at ETH Denver on exactly that topic and on Fluence's potential role in it. But that's separate from the actual training of the models, which is a more intensive computation, more cost-intensive process. So I think with that, we're about to learn a lot more about that exact process and the costs and security benefits of running it with Gensyn. Okay, in 20 seconds. We good? So with that, Harry from Gensyn, give him a hand. Thank you.
Perfect. Cool. Great to be here, everyone. And hands up if anyone got a T-shirt or a hoodie from the back stand. A couple of people. Okay. There's lots back there, and we have to get rid of them. So I'm going to do this presentation minimized because I can't connect to the Wi-Fi here. But if it changes, we'll go ahead and do that. So just to kind of kick off, we're going to talk about kind of three key things today. Firstly, deep learning as a topic area. Deep learning is something which is in the public eye to a huge extent currently. Lots of people are talking about it. Lots of people here are talking about it. We've been doing these conferences for a while, and it's good to hear it kind of coming back into the kind of the limelight. So we're going to define that quickly. We're going to talk about the compute problem, which is inherent in deep learning today, and then finally we're going to talk about what Gensyn's doing in terms of building a permissionless supercluster for deep learning compute. So to kick off, we'll talk about what deep learning is, we'll give some examples, and then we'll talk about the kind of wider market. The easiest way, and I think I described this to some of you over at the stand at the back, to think about deep learning is to think of it as a subset of machine learning, and inside of that machine learning, a subset of artificial intelligence. If any of you have ever done any algorithmic trading, or if you've ever kind of done any sort of logical programming ever, you could make an argument that artificial intelligence starts when you tell a machine to do something, and it's able to operate on its own and execute that task. Simply here, buying Bitcoin under $30,000, which maybe wouldn't have been a good trade. Machine learning takes that idea of asking a machine to do something, but it lets the machine draw the conclusion about when to do it. So specifically, you give a machine lots of data about the price of Bitcoin versus dollar, and then the machine determines, say, using a line of best fit, when the most optimal point to make a trade is. So like above the line, sell, below the line, buy. Deep learning is a subset of machine learning with two kind of key caveats. The first of which is it uses vastly more data, orders of magnitude more data. So if you think about some examples like driverless car, image recognition, you have to have hundreds and hundreds, thousands of hours of a car driving around with the inputs to the steering wheel, to the brake, to the gas, etc., in order to build a network there. Whereas statistical machine learning, classical machine learning typically uses smaller data sets. And secondly, they use neural networks, which are models that roughly approximate the biology of the human brain, but ultimately just allow for something called hierarchical feature representation, which is essentially the ability for each consecutive layer of a network to learn something different to the one before it. To kind of paint a picture of this, Free Blue One Brown did a fantastic overview of how an image recognition model works for a handwriting data set. This is the MNIST data set, if anyone's familiar with it. Essentially, you take an image, you make the image into a vector, and then you push it through lots of layers. And a 4, handwritten 4 equals a 4. You can tell the network that. And over time, a network learns to slowly calibrate the various parameters it has in order to produce, when it sees a 4 it's never seen before, the number 4 in terms of an output. The idea here is you expose the model to lots and lots and lots of data, and over time it slowly nudges down to understand exactly what certain images mean in terms of the outputs. The A kind of more mathematical way of thinking about it is as a kind of loss space. So if you have, say, the image problem, the more you expose it to kind of different styles of handwriting, maybe slightly blurrier images of handwriting, etc., you're able to, over time, find the kind of global minimum in a search space where the model is appropriately generalized to the problem, and you could get a totally new handwritten number, show it to the model rather, and it'd be able to classify it correctly. The trick is, though, as we've said, lots of data, and also that data has to be exposed to the model a lot, and that typically means enormous computational capacity is required. The kind of flip side of this is the more compute you have, the crazier things you can do. So these are kind of, at Gensyn, our kind of 4 favorite examples. One of them is the Neuralink monkey Pong studies, where they use neural networks to process monkey brain signals in order to make a brain-computer interface allow it to play Pong remotely. Secondly, if you think about whenever you're on a video call, many video calls, or video platforms rather, they use a form of compression which uses machine learning to essentially upscale the image. So you can have a kind of identical bandwidth to a normal codec, but using this kind of machine learning codec, you're able to kind of increase the resolution effectively. Thirdly, one that everybody knows recently is ChatGPT. This is the kind of output of an enormous neural network which is trained on the majority of the data on the internet. So the kind of scale of this is kind of quite difficult to kind of frame. Basically, internet scale text data sets put through the model, more than once in many instances, although we don't know yet because the research hasn't been released. And then finally, one of the classic examples of driverless car, image recognition. If you want to look at this kind of more from a market perspective, every 3 months, the average state-of-the-art model size doubles. So essentially, like for like, doubling the compute requirement of anyone using those models. And this corresponds to a roughly $2 trillion market by 2030 for hardware. So it's hard to understate, the speed of advancement in this space, but also the kind of enormous economic kind of consequence of that advancement. So to quickly summarize on deep learning, it uses artificial neural networks to learn patterns. It requires lots of data, and crucially for the rest of this talk, lots of computational power, so lots of compute cycles. The market's enormous, and as we've seen recently with ChatGPT, and we'll continue to see as the world gets weirder, it's going to completely change the modern human experience. So at Gensyn, we're solving the compute problem within this kind of scenario. Let's talk about 3 things. So principally the key issue, which is the price versus scale trade-off. We'll talk about the supply side issues, and we'll talk about the concept of freedom of compute, which is something that Fluence mentioned. So everyone's familiar with the kind of bad guy in Web 2. Many people they don't usually put numbers to it. 61% is the gross margin on EC2. It goes up to sort of 70% on Azure. It can be higher for more kind of bespoke compute providers. Essentially, if you're trying to train something of the order of ChatGPT, over half the cost for training, which is the main cost, is going into someone else's kind of bottom line profit, which isn't very helpful if you're trying to advance the frontiers of deep learning. Typically, when you want to train a large neural network, you have kind of a few options. You can either buy all the GPUs yourself, which is really only an option if you're a large player, or otherwise, you basically have to work with AWS. So for a NVIDIA A100, which is a kind of standard deep learning GPU, on AWS, that's going to cost you roughly $4. If you use a specialized deep learning compute cloud provider like CoreWeave, it's going to come down to roughly $2, but you won't be able to get as much as you could have got on AWS. And if you go even lower, you could buy the physical A100 yourself. The cost is very low, but it's very, very hard to scale. This creates an issue whereby if you want to compete with Google or Microsoft, you have to essentially pay an absolute fortune. ChatGPT, for example, is owned by Microsoft. It's trained on Azure compute farms. The original deal they did with OpenAI was for $1 billion of Azure credits. That's very difficult as an outsider to compete with, and most people are outsiders. Secondly, even if you did have access to that compute, it can be turned off. This is something which is ever present in these conferences. It's something we think about a lot. As neural networks begin to replace not just human decision making, but also speech. I mean, ChatGPT is a speech bot. It is a language model. we've kind of made the we're in the kind of third chapter of technological advancement here. We had originally kind of constitutional biological rights, you can say certain things, have then shifted over into kind of transistors around the middle of the 20th century. And now we're in a position whereby people can be programmatically censored. Models are, being requested by court dictate to have kill switches, put them in the European Union. And there's now, of course, a scramble among all the states in America to enact laws to prevent large language models and their consequences. But more broadly, and maybe more relevant for this audience, there is simply a huge amount of computational resource which isn't being used in the world today. If you were ever like an Ethereum miner, you'll know that the kind of glory days are over. If you're holding on to any of that hardware, if you want to try and attach that to something which is going to give you a yield, your options are very, very slim. And the yield you're going to make is a fraction of what you previously received. It's caused many miners to go out of business. But moreover, it also doesn't provide a kind of incentive for underused compute to find a home serving useful work. So to summarize, oligopolists are extracting fat margins. Even if you pay the margin, it's hard to get the scale. Oligopolists, governments like to censor people, and we've seen that kind of, ad nauseum for the past kind of decade. And finally, there's exaflops of compute which just aren't being used in the world today, which could be kind of put towards useful work. So at Gensyn, we solve this by building a deep learning supercluster. We're a trustless layer 1 protocol, which is solely focused on training user-submitted neural networks. Crucially, when we say training, we don't mean inference. So when you use ChatGPT, you're using the model in a kind of inference setting. It's producing a result for you. We're fully focused on everything up until that point. So all the dollars spent to build ChatGPT and its kind of its analogs. We reckon that the price can be up to or more than 90% cheaper than your standard AWS GPU compute, using an A100 as a benchmark. We're able to maintain security at scale, given a novel verification system that I'll speak about in a moment. And we're seeded with over 50,000 GPUs in our community, many of those coming from disgruntled ex-Ethereum 1 miners. And we're backed by a number of leading investors. So just to touch on our verification problem here, when you think about a model learning, essentially a trivial way to think about it is imagine the model is taking a test. How many mistakes is it making? That's the model loss. And over time, models typically make less mistakes because they're exposed to more data, and they've also made the mistake before, so they're able to kind of correct for it. What we saw with the kind of handwriting example. The issue of training neural networks in the context of verification is threefold. The first is neural networks are very computationally expensive. People in our community spend weeks training individual models. So that's an AWS EC2 instance in the cloud running for multiple weeks on end for one model. Secondly, models are typically probabilistic. They're not very deterministic. So lots of the GPU operations, which have made modern neural network and deep learning breakthroughs possible, are, the speed advances come at the expense of essentially determinism. So if you want to do any hashing, that goes out the window because it's difficult to kind of maintain identical results across different devices. And thirdly and finally, these are just very big models. If you want to kind of parallelize them, if you want to send them around, typically the network overhead is often the bottleneck, although there are ways to get around that. For us, we solve this problem by using a form of polynomial Oracle interactive proof and targeted replication based on that proof. Our thesis is that basically as the model trains, you can monitor the loss of the model. If the loss begins to increase in an unexpected way, you essentially do targeted replication, you pinpoint that part of the process. And because we're using a proof, there's much less overhead required in terms of sending around model parameters and data. Secondly, we also apply contiguous replication over the top of the model training process in order to prevent what we'd call a laziness attack. Essentially, there's kind of two types of attack we're trying to prevent here. The first one's laziness. So basically, someone wants to get the yield for training a model, but they don't want to train the model. That's number one. And the second is vandalism. That's the idea that maybe a malicious actor is on the network. They've seen that you've given your model to the network, and then as a consequence of that, they've decided that they want to, cause a problem. Our system catches and solves both those problems. And the kind of consequences, when you think about that kind of previous trade-off between scale and efficiency, we're able to basically take that very, very cheap unit cost of compute, that sort of 2 cents an hour compute that you kind of see in the Ethereum classic mining pools for an A100, and we're able to take those GPUs and apply them to this much more valuable task at a global scale, a scale which isn't kind of limited by the size of a network. To kind of like paint a picture of this, you can think of there kind of being four types of four types of user in a network. Two on the demand side, and then two on the supply side. On the supply side, you have your kind of classic Ethereum miner. They might be mining Raven Protocol right now. They might be mining basically any number of proof of work coins which are materialized post the Ethereum merge. If you've got an A100 standard deep learning GPU, you're typically looking at 2 cents an hour if you're lucky for maxing out that GPU. Equally, if you're a cloud provider, so let's just say your main business isn't Ethereum mining, it's not even Web3, but you've just got kind of spare compute cycles, you want revenue predictability. We speak of one of the largest data providers, or rather cloud providers in Europe, who for 3 or 4 years actually was a substantial Ethereum miner. They made about 30 million euros per year in revenue, top line revenue, from utilizing their GPUs when they weren't otherwise being used by their customers. These people either want more revenue or revenue predictability. On the other side, you have people who are using EC2 and they're paying through the nose for that same A100. These are real numbers. They almost don't feel real, like $4 on one side and 2 cents on the other side. But this, if you can look at it right now on AWS or the classic pools, this is as of this morning. There are people who are paying through the nose for these A100s. It basically means they can train the models for less time, or they just can't train them at all. And then there are some people who use more specialized providers, but even still, we reckon that the price that we can get it to, including the verification, including the network overhead, results in an 87% and 74% saving, respectively. And of course, the benefit to all of this is you can train bigger models for longer, and bigger models being trained for longer results in much more advanced neural networks, which allows many more breakthroughs in the field. If you're interested in either supplying compute, so let's say you were a miner, or you just actually have a gaming PC, or maybe for some reason you have a number of A100s or other kind of contemporary devices, we'd love to hear from you. Scan the link, the QR code. Secondly, if you're more broadly just a deep learning engineer, or you're interested in training large language models or vision models, then as well, we'd love to speak to you, because we have a solution which will be significantly less expensive than the kind of Web 2 equivalents. That's it.
Thank you. Thank you so much, Ben, and thanks for the swag we have in hoodies and t-shirts at the table. So yeah, feel free to take it. Any questions, guys? Yeah. I think, yeah. Can you?
Thank you for a great presentation. So my question is, when your team got started, what was your strategy to bootstrap and scale the network of suppliers?
Sorry, one more time.
When your team got started, what was your go-to-market strategy, trying to bootstrap and scale the network of suppliers of computation power?
Great question. So we benefited from the Ethereum merge, basically. The Ethereum merge is a kind of a blessing for us, because typically in our world, and I probably include some of the other companies and protocols here today, the supply side, it tends to be relatively, I describe it as like coin operated. So if you're a miner, and we go to the kind of Bitcoin mining conferences, and we were in the various Ethereum mining circles, these people just want money, and if there's a way to get it by buying an A100 and standing it up in a data center or even a shipping container in Serbia, they'll do it. And post the kind of Ethereum merge, essentially the kind of opportunity cost of mining became a lot lower, because they didn't have the Ethereum 1 network to mine on. So that was the kind of first kind of, I guess, tailwind that we had. Secondly, with the kind of huge interest in deep learning, which we're seeing just now, there's demand from kind of hobbyists, from people who don't have access to these large clusters, from small startups as well, who typically get to the end of their kind of AWS compute credit package of like $100,000, and they're like, wow, this stuff costs so much money. I'm bleeding cash whenever I try and train a model, who are looking for cheaper alternatives. And it was basically going after those people on the demand side, and the kind of disgruntled miners on the supply side, which allowed us to get the initial community we have today, which is about 2,000 people.
Thank you. One more question. Yeah, I see.
Hi, it's very impressive. I have one question because I think many people had the same problem before. I used to work for the recommendation system for TikTok. As you know, we have very large models, and we use very stable cloud services to train our model. It trains 1 week, like you said, weeks. But there is one thing we suffer a lot, is that some node will die in the training because of the memory issue, because of the disk issue, or because of any possible issues. So if some node fail, we have to retrain the whole model again. And so in your solutions, it's decentralized, use the resource. I personally think that the stability of the node will be less stable compared with the cloud solutions. So how are we going to overcome with that? What do you think about the ML ops?
Yeah, great question. Also, could you guys turn the speakers up possibly, just for the audience, if that's okay? Thanks. So yeah, basically, machine learning operations. How do we think about the kind of fault tolerance of our system versus the kind of incumbents in Web 2? So there's kind of that you have to kind of bisect that question. There's the data kind of side of it, and then there's the compute side of it. We've solved the data side of it with a proof of availability subsystem in our network, which essentially erasure encodes and chunks data. So it kind of creates a fault-tolerant data availability layer. In terms of the compute side, that's a good question. And it really depends on the model architecture you're using. So the jobs on the Gensyn network are quite small relative to the overall model. And essentially, so if you've got something of the order of maybe GPT-2, so a model with over 1 billion parameters, which takes a long time to train, nowhere near as much as ChatGPT, that model will be chunked into thousands of little jobs. What we do is incentivize each individual node provider to, number one, not go offline. You just can't go offline. If you go offline, you're going to be severely punished for it. You'll lose your stake. But if you do go offline, at the kind of model level, at the abstraction level, you're able to train models in ways which don't require every single individual job to have been completed, number one. And number two, you can also see that the job hasn't been completed, and then you're able to kind of, as a consequence, retrain that job. The cost of retraining is covered by the node which fell off. So as a user, it's more fault tolerant in the sense that decentralized networks tend to be more fault tolerant. However, at the cost of it maybe being slower. So there's a little bit of a speed cost there. It's an issue that we don't see being an issue in the long run as more kind of institutional players join the network, similar to the way that Bitcoin miners have somewhat become institutionalized over the last decade.
I have two questions. The first one is, do you have some metrics showing for Bitcoin mining? For example, we have a farm, right? At which point it would make sense to get rid of Bitcoin and do this work, number one. And the second question is easier. It means, do you absolutely need, using CK proofs makes your project viable, and without CK proofs, it would not work?
Cool. Two good questions. On the first question, the way we think about this is how Bitcoin miners think about it, which is time. It's basically the time to return the underlying hardware. So if you're buying a kind of ant miner to mine Bitcoin, and you're putting it maybe in someone else's data center or someone else's mine, you think, what's the time to return really on the blended cost of the Bitcoin over that period? Usually the number that they go for is between 12 and 18 months. You want to return the cost of the hardware in 12 to 18 months. Our 53 cents an hour estimate bakes in the idea of an individual going out, buying an NVIDIA A100 on the market brand new, putting that in a data center, and then the break-even cost for doing so, including the kind of increased verification time required on a network, kind of shaking out to 53 cents an hour. So at 53 cents an hour, if that's the kind of steady state price, as a Bitcoin miner, provided there's enough demand on the network, you should be indifferent about whether or not you want to mine Bitcoin or you want to mine Gensyn. Lower than that, it gets a bit different. But you have to satisfy both sides of the market. So that's on point one. Your second question was on ZK and whether or not it makes the kind of network, I guess, work. It makes it work better. It's not essential in as much as we could have a dumber, more expensive version of a network which maybe catches less of the second class of attack I talked about, which was the kind of vandalism attack. However, using the proofs that we use, which technically aren't zero knowledge, they're just proofs, but they take some zero knowledge research in polynomial interactive oracle proofs and take out the zero knowledge part to get a speed increase. They make the entire verification system much more A, efficient, and B, robust.
Too many questions. Yeah, let's keep it a little bit shorter, and we can go with 2.
Thank you. I really enjoyed the talk. My question is, besides neural networks, do you think in the future you could use your application to train other sorts of models that require a lot of data and computing power?
Yeah, we think about this a lot, and it's kind of similar to the kind of question of inference as well. People say, inference is easier to an extent, and it's less computationally expensive. Maybe it's a better go-to-market. We think training neural networks is the market to go for 2 reasons. The first reason is neural network training represents a market which is unique in the world in terms of computational expense. It's going to be bigger than rendering, and it already is. It's going to continue to grow much larger. It's something which is foundational to our economy going forward. Many models, once they're trained, have to be retrained, for example. And thirdly, if we branch out to kind of more statistical machine learning models, so for example, XGBoost or like Random Forest, while those are used by people, number one, they typically don't have the same kind of extreme computational requirements as neural networks, which means that the kind of calculus for someone switching off of AWS onto us is a little bit less clear, number one. And then number two, those models as well, we think, for many of the use cases which are coming, we're talking like kind of artificially general intelligent use cases where you have autonomous machines which kind of look similar to kind of androids, or where you have Oracle level supercomputers. This is going to be eclipsed by neural network training. There's another argument about whether or not we do compute like rendering. We think we're better being focused on one very tight vertical, which is neural network training.
Thank you.
Do you expect that all these nodes, do you expect them to hold the entire model, or are you also compatible with federated learning?
It's a really good question. It depends on the size of the model. The short answer is no. For some models, so actually for the image, the handwriting model, the answer is yes. But for for any kind of modern transformer model or language model, over sort of 500,000 parameters, the answer is no. The model would be chunked higher up before it hits the node into a smaller job, so they wouldn't have to hold all the model, and secondly, they wouldn't have to hold all the data either, because the data is erased or encoded and chunked and distributed around the nodes of the network.
And so when you're doing your verification, are you passing through one layer? So this comes back to the federated learning part. So that means that if are you verifying what one node does through its layers? Are you verifying one layer? How is that working?
It's a really good question. The short answer is our thesis is it won't be federated, so it won't be doing federated averaging, purely because federated averaging isn't the way that large transformer models are trained. It would look more like a distributed machine learning workflow, like pipeline, where if you had an NV-linked cluster, it would look like that with verification checkpoints. But the short answer is you could do a federated model on top of that as well if you wanted. Yeah, I can talk to you more about that after. That's a more technical question.
Great. Thanks so much. Appreciate it, Ben. So let's give him a round of applause, please. And coming up next, introducing Prashant from Spheron. We've already had we've been very infrastructure focused, and I think everyone who's spoken so far are building critical building blocks for the infrastructure of Web3, but that doesn't help if we don't have users. And so what Spheron is building is actually they're basically an onboarding effort to bring applications and users to Web3. And so from Prashant, we're going to hear their initiatives to have applications native to Web3 and bring the users that we all want to see into the Web3 ecosystem. So with that, round of applause for Prashant. And I think last time I saw him, he was in. We were in Singapore. It looks like he's come from that climate because he's wearing his jacket inside. So he may be used to a different climate than here. See ya.
Yeah, I'm coming from Dubai, so it's a
go.
really hot weather there. But thank you so much, Tom and the entire Fluence team for having me here. So I'm going to make this entire discussion a little bit more interesting rather than like more focused on the tech side, because a lot of tech people have already spoken about a lot. And as Tom was stating about, like, it's good to build infrastructure today, but it's also is where we start thinking about how we are going to drive the adoption for it. And that is where Spheron kind of kicks into the picture. We are more focused on building the middle layer on top of all of these infrastructure which you guys are seeing today. Today at Spheron, we are proud enough to have aggregated more than around 5+ infrastructure out there. And we are also proud enough, like, one of the best tools out there to host your DApps, launch your computes, and a lot more things. I'll try to dive into much more deeper into it. And if you guys will have any questions, feel free to shoot me up after the talk. So yeah, I'm currently working as co-founder and the CEO of a company, taking care of making sure like Spheron goes to the global stage, and also making sure Spheron also getting into the developer's hand. Now coming to the talk, which I'm going to be specifically talking about, is going to be around improving the Web3 infrastructure accessibility. That is what I'll be talking about. And these are the feature set which you can go ahead and start using today in Spheron, like decentralized hosting, compute, Web3 storage, and dedicated gateway. And believe me, once you go to the Spheron, you will find it very easy to use. So let's get into the state of the Web3 currently. You guys have already heard about a lot about the tech infra, where all of these people are building very core level, module level blockchain, sovereign level blockchain, which is more focused on solving the lower level use cases. But if you see all of those as a use case, these are the current state of the Web3 infra. It's like it requires a high learning curve to go and start using any of those protocols. Lack of automation and toolings. So if I ask you today, it is like to automate the entire server operation of yours or DevOps process, I can challenge most of you will not be able to do it. If you can, then I would love to give you a coffee right now after this particular talk of mine. Highly broken out, which basically means like it is like if you have to launch a DApp, you have to literally go and talk to 4 to 5 different protocols to make that happen. So it's like highly broken out. Token is something which is playing a very vital role. Personally speaking, if I'm a solution architect for your everyone information as well. If I have to integrate Web3 tech into my solution, I'll not go directly with the token model. The reason being because if I go directly with the token model, I don't even have an opportunity to go and explore any such kind of technology before even I start using it. So that is where the token gap kinds of start playing the very vital role. Fragmented in various ecosystem, again, it's like you have to, if you ask me today, I see crypto in 2 verticals. One is called transactional chain, one is called infrastructure chains. Transactional chain, people are the DeFi users and NFTs and DAOs and all of those things. But infrastructure users are more around like storing your data assets, storing your NFT assets, and all of those things. Imagine if you are making a money in transactional chain, but you have to pay for the infrastructure chain, and then you have to go for a lot of token swap here and there, and go to Binance, go to different exchange and get wrecked yourself, and then once you are done with wrecking yourself, then go ahead and stop using the infrastructure completely. So these are the fragmentation which you can see today. Lack of grant dispersal model, and this is one of the best use cases which at Spheron we have kind of built over the time. If you see the infra as such as a whole, it cannot scale if you give out token to normal, like all the developers like that, because they will have opportunity to go and dump into the open market. And the moment they dump into the open market, you know what is going to happen. Your protocol is not going to scale anymore. You are going to be basically giving out free USDC to people to start partying into the parties out there. So that is where the grant dispersal model is kind of a very vital role. And at Spheron, as I personally believe, and my entire team also believes in one thing, Web3 education is very important. And when I say Web3 education, it is basically around infrastructure, because a lot of people talking about DeFi, NFTs, and whatnot, but really you will find people talking about Web3 native infrastructure, and that is where we want to focus on. And that is where our education materials and things are kind of lying around. Coming to Spheron and how we are kind of changing the state of the Web3 infra. These are the couple of things which we do. We are the aggregators. We are building one of the best aggregation out there. What we are trying to do is, let's say if Fluence is building something, Fluence has a serverless model and everything, what we can do at Spheron is we can build a wrapper on top of it so that Fluence can go ahead and start distributing those wrappers to the developers out there within few clicks, so they don't even have to worry about Fluence project as such, but they should be worried about solving their use case. And that is what that aggregation kind of means here. Bridging the token gaps. Today at Spheron, once you log into the system, you don't even require any token to start using any protocols out there. It's very straightforward. Go as a freemium model. Once you start loving the system, then go and start working on the token or even thinking about the token. And that is where we kind of play a very vital role. Apart from that, Spheron currently exists on all the EVM chains and on Solana as well at this point of time. We are scaling ourselves heavily into transactional chains so that we can bridge the gap and bring the money to the infrastructure chain so that infrastructure innovation can be kicked in and a lot of people can start building into that space. No-code dev tools and automation, which is already built in. So you have, if you have a GitHub, if you have a GitLab, Bitbucket, or whatever, you use as your repository, go and configure entire thing as an automation, and it is just a few clicks away. You don't even have to learn anything new. It's just straight Web 2, but underlying infrastructure is going to be utilized as a Web 3. Built-in grant dispersal. So as I spoken about earlier, we have these things. I would love to, I'll not have enough time to basically show that here, but would love to, if anyone wants to discuss deeper into that, we'll love to. But just to give you the understanding how exactly the Spheron grant dispersal model work. So for example, today, let's imagine a scenario. Today, Fluence wants to go ahead and give out their tokens to people who are building over Fluence, but they want them not to dump over a market, right, directly. So instead of dumping into the market, they should be able to use that token to accelerate or use their infrastructure. So what we have done is we have built an alliance-based model into the system where we can create a liquidity pool for ourselves internally. We give out grant to these developers in a virtual system rather than in a real coins. It will be a virtual coin, which is a wrapper around it, and they can just use it in the system itself. They cannot use it outside of the system, which basically means you cannot withdraw it out. And also, by this introduction of mechanism, you also safeguard yourself from a lot of legal troubles as well. So that is where this dispersal model kind of plays a very vital role. And then you can do a lot of incentive mechanisms. So for example, we partner with Akash Network. And when we partner with them, we built one of the coolest feature on top of them was the incentive model. So today, if you want to go to Akash, ask them if you can incentivize us. They will incentivize you via their Akash token by the Spheron, where you can get those tokens and start building on top of them very easily. Education and best support channels. So yeah, out of if you are new to the Web3 ecosystem, if you are moving from Web 2 to Web 3, we have a dedicated support channel in Discord. Go ahead and open a ticket for yourself. One of our team members will be jumping into there and will be helping and making sure you guys are able to shift to the Web 3, and we'll make sure you have a nice and great experience there. So let me play this video. This basically represents how exactly this Spheron works and how we basically make sure that it happens. So here on the left-hand side, there are users. In the center, there's a Spheron. And this particular engine which you are seeing, which is rotating now, it can be scaled horizontally in multiple nodes. What basically means we just don't believe in having a decentralized infrastructure aggregating, but we also believe in making sure our infrastructure is also getting decentralized over the time. And that is how the infrastructure kind of looks like. Our model is very simple. Just imagine you are building a service-based company where on the other side of the company, you have people who have let's say you have nodes which has working capability. You pick those nodes. What those nodes do is they just upload the data to the specific providers wherever they want to. And Spheron, what it does in the middle layer is it makes sure it facilitates that particular process so that our users has a very great experience there. And while doing all of these things, we are building a nice incentive model for all of the people who can basically participate and start scaling themselves. And as you can see, on the user side, user can be on Polygon, Optimism, Arbitrum, Solana, or Avalanche, or wherever we are, and just start accessing any decentralized infrastructure out there. Again, just to pointing out, like it's again a chilling point where I just want to chill as well, more Spheron as well. Why is Spheron today? Is because we are chain agnostic. We have all of these automation works. If you have a D app which you want to accelerate using, and you want to make sure like Web3 infra kind of getting used for your D app, go ahead and start using Spheron. You don't even have to have off-ramp your crypto to make the payment for your infrastructure costs. So go ahead and start using it. And most importantly, we have been building this particular space for the past 3 years. So we have learned a lot of problems which infra companies might face in coming days if they are building on top of it. So we are well positioned to make sure we take the infra to the mass adopted on the developer experiences side. Coming to our achievements, which I just wanted to focus on as well, what we have done so far. We have onboarded 3,300 plus developers. We are very heavy in India. If you go to India and ask about us, most likely you will get to know about us. So most of the developers we were targeting in the Indian space. Now we are expanding globally as well. We are getting into Vietnam. We are getting into other Asian market. And we'll make sure in the next 1 year, I'll show you the number what we are kind of looking for. But that is something which we are kind of targeting for. We have more than 17,000 plus unique web application deployed so far. Serve more than 155 gigabit within last 3 months. We started calculating this data from January. 100 plus unique domain, which means like 100 plus new businesses are getting served via Spheron gateways. 50 plus active compute, and this is why I wanted to mention it here, Akash as well, so that the moment we integrated them, we had around 50 plus compute, which has been currently active. Via Spheron itself, we have around 2.5K plus AKT been distributed so far. We have 10K AKT into the liquidity pool as well, where we are planning to distribute as well via Spheron, this one, our grant dispersal model. Coming to the next, what we are looking for to achieve, and these are the couple of things which we are on our track list. Product is solid, everything is on the line. The next thing is we are looking for to onboard next 20K plus developers across the space. When we say onboard, that basically means like they should be, by any chance, they should have one GitHub unique accounts. They should have one GitLab or whatever unique accounts. That is what when we call them as a developers, or else we don't. If they have certain commits also into the system, then only we call them as a developer. So that is what those numbers kind of represent like. And that is where we'll be working. We have all the plans in line to make sure like we are able to reach that number. And we'll make sure by the end of this year, you will, most likely next year when I'm back on the stage, we'll have those numbers in-house. And coming to other part, as I said, education is something which we are most focused on. We are going to be launching Spheron University soon. And the focus of the Spheron University is not to talk about DeFi, not to talk about anything else. Focus is solely going to be around talking about infra providers and how exactly the Web3 infra can solve the bigger problems and issues which most of people before me were talking about, like censorship and all of those things. Spheron DAO, since if you have seen that architecture earlier, there was a node which was sitting around, and that was the DAO part where DAO wanted to introduce and make sure like these DAOs are able to make sure and run these dedicated gateways. And as a founders, we are running those gateways. More infra partners, we are currently working to onboard more infra partners so that we can provide various other features on top of it. So for example, today we don't have a serverless execution yet. So that is something which we are kind of working on. Most likely that will also be done. The most important part is the infra marketplace. So today, if you have to launch, I'll be very honest. So if you go to the market, a lot of people have a WordPress application, right? And one of the best places to capitalize the market is also to provide the support of the WordPress applications. So infra marketplace is a place where all these developers who are building over a Web3 infra can go and submit their templates, like they can go ahead and sell their templates as well. For example, if they have built their Docker, which can run on Akash network, or they have built a user interface which can be deployed on Filecoin or IPFS or RV or wherever, they can go and monetize that by putting that over an infra marketplace. And other side of the user, they can go ahead and buy it and immediately start running it without any hiccups. So yeah, that is it. Thank you so much. I believe I have not bored you a lot. So again, if you love what we are building, we'd love to connect with you. Spheron HQ is our headline. We have a foundation which runs at Spheron FDN. And yeah, so let's bring million users and million developers on the Web3 infra in coming days. Thank you so much.
Yeah.
Hi, thank you. It's very good presentation. I just have one very simple question. So, I didn't really get clear about your decentralized network, the details of the technological side. Do you have your own decentralized network? Or in other words, could a normal miner join your network to provide the services to get some coin incentive? Or your decentralized network, your infra resource is built on top of other network? Yeah.
So generally, let me just go back here again. This is where I was kind of showing that. If you see this in the network, that part, this part which is their nodes are there. Those nodes are nothing but we call them as a worker nodes, and their job is to basically just imagine this way. In this room, we have 100 people sitting. Out of that 100 people, 10 people owns AKT token, 10 people owns Fluence token, 10 people own RVIV token, or whatever token they own. What we tell them is, if you have these tokens, which are just lying around with you, and you are predicting that and speculating in the market to basically pump that token up so that you can dump it over the market, instead what you can do is like you can use that token and generate yield for yourself by participating in the network and lending your token there. So that these workers can, what they can do is like they can use your token to upload these assets to these particular decentralized infrastructure. And once they do that, they will get incentivized. And as of now, we have not yet built the incentivization layer, but our aim is to build some incentivization layer where all of these developers all the nodes providers who are becoming the active web worker here, they are getting incentivized either in the Ethereum token or either in the stable coins or either in Spheron token. Who knows how exactly we will design it. But that is what our long-term aim is. But at this stage, we are more focused on driving the adoption in terms of understanding and letting people know about Web3 first, rather than just introducing the token at the first.
So, okay, we can talk that offline, yeah, if you don't mind.
Any other questions? I saw one more hand. No? You want to ask something else, right? All right. Okay. Yeah. So we have time for questions because Wook is like for a couple minutes he's out.
Oh, break. All right. Well, thank you, Prashant. Yes, we're done. Thank you. Give a hand to Prashant. Thank you. And just, I know Prashant has come from Dubai. Our next speaker has come from Ecuador, but we've just lost him for a moment. Where is he? I just saw him. He was sitting right there, and he vanished. Vuk, who's building Filmine, which is a protocol for basically compute on the Filecoin network, for both running decentralized hosting and storage that basically allows for contribution of storage capacity and the staking of Filecoin. Oh, and there he is running in. This allows the staking of Filecoin on Filmine to basically enhance your reward profile. So fresh from the Ecuadorian jungle, please welcome Vuk. I think that's the web link. There you go.
I'm good.
Right?
I just finished the slides, so bear with me. And also ignore the Solana hoodie. They gave me the hoodie for free because they were closing the store in Miami. And it's pretty good. Anyhow, yeah, I thought I would talk about a bit of a different topic. Usually I would talk about decentralized computing, coordinating all the jobs that we heard about today, and figuring out how to take like a job from a network and deploy that into a particular provider. Today I'm rather going to talk about like what are the implications of all of this, but on a token economics level, and how to think generally about these networks. So first, what do we actually mean by Web3 in this context? Anyone has an idea? Yeah, I mean, generally Web3 was framed by Parity, I believe, in 2018, and it was kind of a mixed term. It was really cool because 3 is larger than 2, so everyone thought this would be actually the next thing. But actually, there is a lot of ambiguity on what Web3 is, and I think that we are coming now to a point where Web3 is actually gaining like a sense. So it's not a one network where you have transactions that are happening with some consensus. It's rather focusing on something that provides more of a utility. So you have networks that provide a particular utility. So you could imagine Filecoin being a utility network. The utility of that network is the storage. So you provide the storage, and you have utility providers, and the utility providers in that context provide the storage. You could have Lipeer network providing the encoding. You could have the Fluence network providing some generalized compute. But those are utility networks. We're not talking about Solana. We're not talking about Ethereum. We're talking about networks that can provide a particular utility. And in those networks, always you'll have like 2 main roles. One is the utility provider, and the second one is the token holder that is basically a stakeholder in the entire protocol. So if we look at those 2 roles, you have resource providers. So those are folks that are basically providing the hardware or providing like the software that is giving that utility. So in the case of Chainlink is providing the feeds. That's the utility that the Chainlink network provides. In the case of Lipeer, again, like the encoding and so on, well, the token holders are just holding the tokens of those individual protocols. Now, how does a utility provider look like? These are utility providers that can do like some kind of encoding, some kind of computing, and so on. Those are also known as miners, but the miner word is also used for a bunch of other things, so I'm going to try to avoid using it. But you could imagine a utility provider like this, or a utility provider like this. These are more frequent in the Falcon network because it's not enough that you have GPUs, but rather you have some kind of storage, but also you need some computing because you need to do a lot of cryptography that is necessary to onboard data to the Falcon network and so on. While token holders are basically, yeah, just shillers and like people that just believe in the network and want to actually be part of that journey. So how does a resource provider interact with the token holder? So usually you would need some kind of liquidity as a resource provider in order to provide that utility. Let's get a bit deeper into one particular protocol, which is the Falcon network. So the Falcon network does provide 15 exabytes of capacity today. This is committed capacity that is being proved every 24 hours. So there is a proof of every sector of 32 gigabytes that particular piece of data is actually stored on the Falcon network. You have a ZK snark that is done in the background. 3 petabytes of data are being onboarded every day. And very soon, like it will have EVM compatibility. But the point is that in order for these 15 exabytes of capacity to be on the network available for everyone, you need a resource provider. That resource provider needs to do a set of activities. They need to first provide and commit a particular amount of storage. So let's say it's 32 gigabytes, which is like the size of a sector. The sector is very well known in the Falcon ecosystem, but I'm not going to get deeper into it. Then what the storage provider needs to do is they need to commit a particular amount of collateral. So like you need fill that will be locked as collateral in the case of the storage provider going offline. And that collateral is not small. Like you'll need to commit 0.2 fill just as a commitment. And if you're really storing data, you would need to commit 2 fill. 2 fill is actually $20. And that's for 32 gigabytes of data. So the requirement of the liquidity is super high. Yeah, just to walk you through how the protocol actually works is that once you have committed the collateral, then you have like 24 hours. You have the storage power. The storage power is used in the same way as hashing power on the Bitcoin network, you're getting rewards because you have the storage power. And every 24 hours, you need to generate another proof so that you'll get like the rewards for the next 24 hours. And basically, in that way, you're getting block rewards from the inflation that is happening on the network. Now, of course, there is also risks involved. The collateral is not there just because of the sake of the collateral. It's actually there to have the ability to punish a particular storage provider if they go offline. If the data is really not there and they have committed that they are going to store the data for a particular amount of time, they'll get penalized. So what will happen in that particular case is that the storage provider fails to send the proof. So they have a particular grace period in which they can not get rewarded, but still not get penalized. And ultimately, they are going to start getting slashed. And if they are offline for a long enough of a time frame, they are just completely going to get slashed. So like all the collateral that they have is just going to be burned because they are not providing the utility which they have committed that they are going to provide to the network. Okay, but this is just one instance of like a Web3 protocol. What about the other ones? Guess what? Most of the other ones have like a similar model, and the reason for that is that they need an economy that is self-sustainable, because if you don't have a demand for your particular governance token or whatever utility token you're using, it's super hard for you to build like a sustainable economy. So in the case of Lightyear, you have the abstraction of an orchestrator, which is basically someone that would get jobs from the network and would execute those jobs. Now, the orchestrators can run also the workers, which are basically doing the encoding, or they could just offload that to someone else. But similarly, you're basically, as an orchestrator, staking the tokens, and because you have a particular amount of tokens staked, you're able to get a particular amount of jobs. So you always want to be staking more, so you get more jobs, and with that you increase the utility which you can provide, and with that you increase the reward that you can generate. And of course, when you return the results to the network, you're just going to get rewarded by the network. Okay, does anyone see a problem potentially here? I hope yes, but I hope that everyone is timid. Ultimately, the issue here is that liquidity is linearly dependent, the utility is linearly dependent with the liquidity, meaning that in order to increase the reward, and with that also increase like the utility that you're providing to the network, you need more liquidity. And now if you roll back and think who the utility provider is in this particular case, it's a miner. Why would a miner care about holding tokens? They don't. They care just about generating profits and just growing their infrastructure business, which is fine. Like most of the businesses today work in that particular way. But all of the networks that we have today are basically designed more from a top-down approach where the economy is actually dictating how the protocol should be built, rather than interviewing particular like personas and trying to understand like what a miner would like to do. The miner doesn't care. And generally, like everyone that was designing the Web3 protocol couldn't care because they had to think about the economy. So yeah, generally the reason for that is only the fact that you need to create enough demand for your utility token so that your token is not going to go to zero because you're just inflating your economy. Because if you also zoom out, like most of the economies in Web3 need to have some inflation. The inflation is there not to screw up like the existing token holders, is there to incentivize the utility to be provided on the network. And most of the networks are just going to gravitate towards this model. I haven't seen anything different that is not actually like using the utility token and just pushing a lot of demand on it. But how can we actually solve this without changing the core protocol? Because that's most likely not going to happen. Yeah, that's something I'm super focused on, and that's basically what we're building. We're building staking for Web3, and when I say staking, there is no staking in Web3, because like most of those protocols do require a utility to be provided. So when we say staking, it's not like Ethereum where you just stake directly in the node. You actually need to coordinate a bunch of jobs that will be executed on those networks. And when those jobs are executed or the utilities provided, like in the Falcon ecosystem, you're going to get the reward, and then you can do something with that reward, and that's how you generate the yields. In the case of the Falcon network, basically you have a token holder, which in a way just stakes in a particular storage provider, and because you're generating the rewards, you can generate the yield. Now, of course, this is how everyone thinks about staking. Actually, it's a bunch of other things that we had to figure out just to make it possible, because ultimately you need to do a bunch of things to provide that utility. And the better job you do to provide that utility, the better the staking protocol is going to be. And with that, also the higher yields that you can produce are going to be. So how it works, the token holder just stakes in the protocol. The tokens get distributed to the utility providers. They use the liquidity to provide the utility. And then the protocol generates rewards, and everyone is happy because everyone makes money. So yeah, it was super fast. By the way, like I have another set of slides on the computing front. This? Yeah. Oh, this one? Yeah, I thought it was me. This one or the other one? This one. Okay. So token holders just take in the Filmine protocol, which is the protocol that we have built. The tokens get distributed to the utility providers, also known as miners. The miners use those tokens to provide more utility. Because they provide the utility to the network, the rewards are generated. And because the rewards are generated, they get funneled to the protocol, and then they get distributed to the individual parties.
One minute, I am afraid of.
Yeah. So I'm going to start with this, and I have a lot of backup slides that I have assembled for other stuff that I'm working on. So in the Falcon protocol, in order to onboard DEA or commit capacity, you actually need to do a lot of cryptography. That's called proof of replication. It does last like 4 hours in memory, and it does require like a full core, and then you need to pass it to the next process, and the next process requires GPUs, then you need to pass it to the next process, requires some IOPS, then you need to pass it to the next process, requires, again, a GPU. So there is a lot of cryptography for this to work, because you ultimately had to balance out between having a lot of compute happen in the beginning, but proofs that are sent frequently, like every 24 hours, be lightweight, or do a lot of compute like every 24 hours. So most of the compute was actually pushed on the onboarding phase. Now, this is just like a picture, but actually how it looks like is, let me see here. It's actually like this. Oops. This was the next slide. Yeah, actually, and even this is like high level. Like under this, there is another layer. So basically on the right side, you have the storage providers. Then you have like the compute providers that are helping us onboard data. Then you have the ZK snark producers. And like all of these are super different, because for the middle process, you need a lot of IOPS and a lot of memory, and you need like server grade CPUs. The networking needs to be super good because you're transferring a lot of data. You can see that you're transferring 32 gigs between like that provider and the storage provider. And then like you can just offload the snarks to someone else. And that is basically just a GPU activity, which a Ethereum miner could do. And then that gets back to this process, and then it gets back there. Guess what? We built all of this just to be able to stake tokens. So we actually started like as a staking protocol, and I thought I would do cool DeFi stuff, and actually we spent a lot of time just building infrastructure to make it possible. So I think this is going to happen in the other protocols as well. We are looking at Lightbeer. We are looking at many other protocols that are doing snarks. And this is super interesting. But again, like it's a lot of deep technical work just to be able to like do a simple activity on the first layer. Okay, the question was, is this still considered decentralized? Yes, absolutely, because we are not the ones running these nodes. We are a startup building software. I mean, I love computers, don't get me wrong. We have a lot of servers, but again, like we are trying to build protocols that can be used by everyone and everyone can participate in them. And even then, the question is it really decentralized? Depends how you build the job queues. So if the job queues are decentralized enough where you can actually get the jobs from the queues and execute that, commit that you're going to execute, and then finish the jobs, yes, it's absolutely decentralized enough. And the question is where you want to put the line on the decentralization. And I feel, yeah, that's something we'll figure out as everyone is building in the space. By the way, there are many similarities on what we're doing and what the other teams are doing. So I think what we are going to see is like a more generalized protocol that is going to merge all these protocols. I was hoping that's going to be me building it. I still hope, but like I have a lot of work on the DeFi stuff, so maybe someone else can do it. But yeah, super fun. Let me get back to this slide, which was the most important one. For the first time, we are hiring. We need like product people and like a protocol engineer. We are a team of 10 people, and we are funded by some of the best funds in the space. Thank you so much.
Great. Thank you, Vuk. Great. We've got our very last presentation right now. Nico is on his way up from Streamr. This is the last piece of infrastructure we're going to be talking about today. Critical piece of it, it is the decentralized data streams. And I think we're all accustomed to receiving data streams. All of the financial world right now is accustomed to receiving proprietary, centralized data streams. Having decentralized data is obviously critical because it eliminates a point of failure and a point of censorship. So as we think about building this decentralized world, we've got compute, we've got key pairs, we've got staking. Streaming is a key piece of this. All of these pieces need to be in place to build this decentralized world. So with that, I'm going to turn it over to Nico.
Hey guys, how are you doing today? I'm Nico. I'm the developer relation engineer of Streamr. And today we're going to talk about the decentralized real-time data network. So I'm going to start off with a video. I hope it works. We'll see. It does. Okay. Okay, there's no sound, but just read the subtitles. Okay, this looks a lot cooler with sound, I promise. Okay, let's just start and go to the first slide. Okay, so what is Streamr? We are a decentralized P2P network, and how that actually works, I will explain in the next slide. But essentially, we have topic-based publish subscribe system And if you haven't heard of this, don't worry. I'll explain that in the next slide as well. Essentially, we stream data to an Ethereum accounts in real time. So you can get your data from A to B in a decentralized manner. That's Streamr in a nutshell, really. So streams, topics, subscribers, publishers, what is that? I don't know. Who's heard of PubSub before? Okay, so basically no one. Well, if you have heard of it, streams are essentially topics. And if you haven't heard of it, think of it as some sort of a list where you have publishers that write to that list and subscribers that read from that list, right? So you have, for example, this weather station here that is publishing data, writing to this list, to this table, to this stream, however you want to call it. And then you have the subscriber that can then read data from that list. So for example, you have a JSON where you have temperature, humidity, all these kind of things. And then you have this application that then reads this data and consumes it and maybe displays it in a dashboard or, I don't know, shows you the weather forecast, right? So this is kind of streams in a nutshell. So here we have an example stream from Ultrasound Money. And what this does is it streams the Ethereum 2.0 stats, burn stats, every minute. So you can see here, you've got like 48, then 49, and the timestamp. Every minute there's data getting published to this stream, and then someone can just kind of subscribe to that stream and read from it, right? Now, how does this work? How is it decentralized? How do we get the data from A to B? If we zoom into our network, we've got this example stream here, and essentially it's a topology of 30 nodes at the moment. The Streamr network is made out of over 5,000 nodes at the moment, but we are looking at one specific stream topology. Topology is just another word for network constellation, so how the nodes are connected to each other. And in this case, as you can see, most of these nodes have 4 connections to each other, not more than 4, and they have these neighbor nodes. And if you publish a message, it gets kind of distributed over this whole topology network. How this works, I'll show you in the next slide. So we zoom into this Denver node here. You can see these his neighbor nodes displayed on the map. And if I now want to publish data, right? Let's say this Denver node publishes weather data. It wants to publish weather data, so what it does is it sends this message, this data, to all its neighbor nodes, including the one here to Lisbon, which we're going to look into a bit more. So it sends the data to the Lisbon node, and then the Lisbon node sends it to its neighbor nodes, and so on and so forth, right? It's like a chain reaction. And it kind of floods the network with this message right here, but only within the stream topology, not outside with the over 5,000 nodes that we have. So we don't publish the message over this whole network of 5,000 nodes right now. So if you have, let's say, this weather app, you don't want to consume a random data stream, for example, fridge data or some other data, right? You just want your weather data, so we have a noiseless network. There are only streams, there are only nodes that are interested in that stream, which are going to receive the data. So that's the scale. Well, we did a test of this network with over 90,000 nodes in, I believe, 85 countries. And yeah, in over 85 countries all over the world. And yeah, the results were quite interesting. So I just told you, right, we have around 5,000 nodes in total, like globally. And we did this testnet with 80,000 nodes, so it's quite impressive. And what we found is that the mean propagation delay, which is kind of the delay until a message arrives at your node, is around 400 milliseconds. So it doesn't really exceed this 400 milliseconds. So does it scale? I would say it does scale, because 400 milliseconds is quite nice for a decentralized P2P network. And yeah, here you can see it's kind of converging. Right, so Streamr network properties, fast, scalable, real-time. It is permissionless and censorship resistant. It's tamper-proof, end-to-end encrypted. Talk about that in the next slide. And it is free to use, so anyone can use it. Anyone can kind of, create a stream, connect their nodes to it, and then start streaming your use case, essentially. So yeah, access control and security. It's a public network. It's how do we contain the access, and how are we secure? So I just talked about this P2P network and decentralization and everything. So it's not it's not a blockchain. I haven't talked about any blockchain, right? So how do we use smart contracts and the blockchain to utilize this access control is, with a smart contract on the Polygon network. So what we have is a stream registry, which is essentially a smart contract that keeps track of all these streams and the addresses that can stream data to this stream, so publish data to a stream or subscribe to a stream. Let's say you have a chat room, right? You don't want anyone to just publish messages to this chat room, and you also don't want anyone to subscribe to this data, right? So you kind of need to keep track of the access. So this is done in this smart contract. It just kind of registers, okay, this address is allowed to read, and this address is allowed to write onto the stream. So in this example, let's say the subscriber node gets data, right? And it is encrypted. So it's like, okay, I need to read it, but I don't have a key. So it needs to ask for a group key from the publisher node, and then the publisher node is like, okay, well, let me first check if you actually have permission to read from the stream. So it asks the smart contract, does 0xabc has permission? And then the smart contract says, yes, it does indeed have permission. And then it sends the group key to the subscriber node and is able to read from it. All right, so again, let's recap what's happening off-chain. Off-chain P2P data channels. So this is where the data gets sent from A to B. And on-chain is the access control and who gets to read from the stream, who gets to send data to the stream. And yeah, network security. So in an ideal scenario, everyone's honest. No one would leave the network. Everyone would stay online. But in a real-world condition, we all know we have some malicious peers. We have people that want to harm the network. And this is how we kind of counteract. So we have two main attack vectors at the moment, which is one, the Eclipse/Hub attack. If you've never heard of that, that's essentially when nodes or malicious nodes come to the network and connect to, you saw the Lisp node earlier, right? It has like these connections. And if it's only connected to malicious nodes, and they would be like, oh, I'm not going to send data to you, or not going to let data through, you kind of disconnect the node from the network. How do we counter this? This Eclipse attack and this Hub attack, we don't let any node connect to, we don't let the nodes choose who they want to connect to. So if there's a malicious node joining the network, it can't just say, I'm going to just connect to you, and then I'm going to take 3 other nodes and just connect it to you, so you're not able to connect to the rest of the network anymore. You can't choose, right? So it's done by an algorithm. that chooses those connections randomly. We also have the DDoS attacks. So, you know, if the network gets flooded with a lot of messages or data, and it kind of takes away the bandwidth, and there's no room for actual data to flow through, then we have a DDoS attack, and we measure this by restraining this topology to only the streams, right? So the data doesn't get distributed over the whole network. So if one particular stream gets attacked, it's not the whole network that gets attacked. And then, of course, security measurements is also the redundancy. So we have a lot of peers, and there's actually good nodes in the network as well. Right. Okay, I'm coming to the end of my presentation. So if you want to build with us, we have this Streamr client. So if you want to integrate our technology, we have this npm package. And here you can just npm install into your Node application and then write some JavaScript down. For example, here, can you see the mouse? Oh, yeah. So streamer.publish, for example, you just kind of publish this object. Hello world, for example, you just publish it. And here you can then subscribe to messages from that particular stream. And if you want, and you're a builder, I highly recommend to check out our docs at docs.streamer.network. There's some quick start guides, how you can just get started and check out how it works. You can also just talk to me. I'm happy to help. Yeah, and what can you actually build with it? Mostly real-time data messaging, dApps. So that could be IoT applications. I talked about this fridge earlier, so smart home is great. Maybe you have car data that you want to share. Maybe you have a chat app, which we built actually right here, which is called the chat.app. And it's actually going to release tomorrow as a beta version. And yeah, essentially what's happening here, by the way, is this chat right here, this chat room is one stream. And then we keep and then you can log in with your Ethereum account and send messages to this stream or to this chat room if you have access to it, right? So it's almost like WhatsApp, but it's peer-to-peer and completely decentralized. So that's quite a big deal because everyone and their mom has a chat app nowadays, but Streamr does this peer-to-peer and decentralized, which is kind of cool. Right, yeah, if you have any questions, you can either reach out to me via Telegram. Again, I do developer relations, so if you have any developer questions, reach out. And if you have any partnership questions, it's better to reach out to Matthew, who's our head of ecosystem. All right, awesome. That was my presentation. Thank you, guys.
Thank you so much. Yeah. Any questions from the audience? Yeah, I see one hand.
Thank you. How do the nodes make money or get compensated?
So how do Streamr gets money? Or?
No, the nodes.
The node? Oh, it doesn't. So essentially, the nodes themselves are your application or your IoT device. So you kind of become your own, it kind of becomes its own node. And this makes up the network. This is kind of peer-to-peer. So if we both would create a chat room where we want to communicate to each other, my phone becomes a node and your phone becomes a node. This is how it works. And if we have a chat all over the world and it's not just this Wi-Fi network, it's a node would come up in Australia, for example. So this is kind of how it works.
Yes.
So I saw that you launch your tokens. Can I know what is the usage of the token?
Mm-hmm. The usage of the token at the moment is used for broker nodes. And so I didn't put this in the presentation because we were a bit short on time. But essentially, we have this bounty contract for node runners. So if you want to run your own node to provide bandwidth to the network, to a particular stream, you get paid by token, and this is how we use the data token.
Hi, do you use any libraries like libp2p or any protocols like Waku or XMTP to build your product?
Ooh, I don't know that, but if you want, you can just send that question to me, and then I will just ask the network team.
Sounds good. Thanks.
Feel free to contact Nico directly if you have any other questions. Yeah, I knew that. All right, so I think we're finished. Yeah?
Great. Well, thank you all for coming. That concludes today's program for the Decentralized Summit. So thanks everyone for coming, and thanks to each of our presenters, some of whom are here, some are not. If you have interest in talking about Fluence, Bernard is right there, Chief Scientist, and we'll give a big round of applause to Nadia for organizing all of this. She deserves all the credit for making this happen. And appreciate it, and hopefully we'll see you guys around. We have a variety of other events for Fluence coming up. Nadia, do you want to go through some of those upcoming events?
I think that I will just ask you to come for a workshop. It is mostly for developers. So if anyone want to try and build on top of Fluence, so please come on the 1st of March at VIP Hotel.
And our breakfast is when?
And breakfast is also March 1st. So yeah, we should have slides about that. Yeah, so the easiest way would be to join our Twitter or Telegram chat. There's all the information about upcoming events. So yeah, we'll be here for the 2 weeks and see you around probably.
Great. Thanks very much, everybody. Bye.